Thanks very much, Colin. Can I throw this open for questions, everybody? Any comments or questions on what Colin's been telling us?
I just wanted to clarify something you said towards the end. First of all, what you did with the phase galaxy and the lensing is beautiful. But just to clarify what your point was at the end is that the universe, there's a certain limit to our perception, which is the Hubble distance. But if somebody else is standing a million miles, you know, along the x-axis from me, their universe that they perceive will be the same size, but it'll be shifted a million miles over, so to speak.
Correct. Absolutely correct. The Hubble horizon, as I said, it's a virtual horizon. It moves with the observer.
But the universe itself is infinite.
Well, it could be. We don't know. I mean, DeSitter space is finite spatially, but infinite in time direction. You take the space-like cross-section across the middle, it's finite. It's a sphere, radius, whatever it is, A.
Okay.
Free sphere, yes. And it's flat. It's flat.
I was wondering what the fifth dimension is in the DeSitter space.
The DeSitter space is only 4 dimensions. It's 4-dimensional space. I drew it as a sphere in Minkowski-fied space. So it's like drawing the 3-sphere as a sphere in 4 space. The sphere is only 3-dimensional. The ordinary sphere, our sphere, or sorry, a 2-sphere, drawing it in three dimensions. It's 2-dimensional, but you draw it in 3 dimensions. And the DeSitter space is a 4-dimensional sphere in 5-dimensional flat relativistic space, Minkowski.
The X, Y, Z, and T dimensions are observable.
No, wrong. T is observable. X, Y, Z, and W are 4-dimensional space in which we have a 3-dimensional sphere that we live in. X, Y, Z, and W are dimensions for 4 space. Right? It's like saying I'm on a 2-sphere and I'm in 3 space X, Y, Z, therefore they're observable. But I don't see those on the 2-sphere. I only see 2 dimensions.
See, can I just jump in 1 minute here?
Yes.
Okay, when we are taught as small kids in mathematics, undergraduate, a linear dimensional space has to be linearly independent, okay? And when you satisfy that condition, my X, Y, Z coordinates satisfy that condition. So that's why I can say anything that you give me in my hand, a geometrical structure, I can take away R theta phi, X, Y, Z, whatever we want to call that. They're mutually orthogonal, linearly independent, I can do that. The moment you go away from that, even for the time, I have argued about this in my previous talk and we wrote a book about this, even the time does not satisfy, the time is not even an observable independent. Time observation depends upon your coordinates. If you don't have the space, you don't have time.
Correct.
So then going further to a general dimensional Minkowski space makes it even worse.
Yes.
Mathematical, it doesn't even satisfy the linear independent condition of mathematics. Basic rigor is lost. I'm done.
Let me try and explain it in a different way, Pete. Imagine you're sitting on the surface of planet Earth, and I can set up a chessboard or something here, which I could call XY. But my chessboard is in fact slightly curved because it's a perfectly smooth chessboard, my chessboard, which is an exact surface geodesic. So it's actually really slightly curved. So our XYZ is like a patch. So what you can do is you can say that chessboard, I can patch a Cartesian frame onto the surface of what's really an R theta phi Earth. So I have a patch which coincides at the point where the two things hit. But in reality, the megaspace is really is really not an XY plane, but it's a theta phi plane, which I'm sitting on the surface of the Earth. So you have a patch between the theta phi thing, which is really part of a sphere, or the surface of a sphere, and the XY thing, which is my chessboard sitting on the table. So that's a patch. So in the DeSitter space, you have W, X, Y, Z, so there's some sort of thing that, but we're only seeing 3 of those dimensions because we have this constraint, and that constraint is that the whole of space has this cosmological constant, which a higher dimensional being could observe as being a curvature, but we can't because we're embedded in it, And we are ourselves, the bits of us and everything else is locally curved according to that extra constraint, which is the constraint that w squared plus x squared plus y squared plus z squared equals a squared. So by doing that, you're coming down a dimension, but the dimension is on something which has an inbuilt curvature, which is the a squared part of it. Curvature is perhaps the wrong word there, but has an inbuilt constraint, which is the a squared part of it. And Colin will correct me if I'm talking, if it's even more subtle than that, but that's at least my way of looking at it.
No, that's absolutely correct, John. Thank you for getting me out of trouble.
Pleasure.
I wasn't explaining it well enough.
So is that the same? So I was just imagining you're saying that the reason we don't observe the W dimension is because it's on such a slow curvature.
Exactly. The W dimension, we're living in something which is actually three-dimensional because if this postulate is correct, that we are living in a DeSitter space, which, I mean, Colin's made a very good argument for it. I don't agree with Colin entirely. I mean, I look at things, we all look at things in a different way. In fact, I look at a different thing way at 9 o'clock in the morning to 9 o'clock in the evening, depending on which hat I'm wearing and what I'm trying to think about. So it's not that I have a particular view either, but Colin's view is not my favorite one, partly because I'm completely ignorant about it, except for what he's just explained to me pretty much. so of course I'm not that familiar with it, but that's the kind of thing we're talking about here. It's a very, very locally small correction to a three-dimensional apparent world in which we live, even if it is underlying four, or if you like, five-dimensional, and you have four-dimensional space and one of time in the DeSitter space. So it's a five-dimensional thing with an extra constraint, and that means that you're trapped inside this constrained world by this constraint and you can't see it. So it looks then 3 + 1 dimensional, not 4 + 1. If Colin is correct, and this whole thing is best described by having 4 spatial dimensions and 1 time, and not, for example, 3 space and 3 time, or lots of other things that have been brought up, or 11 dimensions where some of them are curled up so they'll be invisible for all time for any possible conceivable experimentalist. But, you know, whatever turns you on for the model you have here, but these are just models.
Correct. Mathematical model.
Yeah,
Don't forget, this is everything I did today was mathematics. There was no physics there, apart from a few experiments, apart from a few observations. We got all these wonderful observations.
There's no way to say that this W dimension has any similarity to either time or our normal 3 space dimensions.
No, it's not part of that. We're in W, X, Y, and Z, but we only see 3 of them. So W is just as good as X, Y, or Z. You could say the actual space we're in is not W. It's like the argument, you know, the argument Einstein sitting up at the board and he's trying to find the equation that describes his stuff, and he writes down E = mA squared. And he thinks, no, that can't be right, so he crosses that out. And then he tries a more sophisticated equation. He tries E = mB squared. And he thinks about that for a bit, and he thinks, oh, that's better, but no, it's still something not quite right. So he crosses it out again, and then writes down E = mC squared. He said, yay, eureka! There's nothing special about C or X or Y or Z or W. It's just a set of, it's just maths. It's only maths. It's time's different to X, Y, and Z. Yeah, because
time and space are perfectly intermingled in special relativity.
Go
away and read special relativity, learn about it. It's
yeah, but
correct.
only one of them is real. The others are imaginary.
No, it's the other way around.
Yeah, well, some people think that. Yeah, some people think that 3 are imaginary and 1's real. Other people think that 1's imaginary and 3 are real.
Whatever turns you off.
ICT and all that. But I've seen papers on ICT. I read one paper about 30 years ago called I forget who it was by, but actually I think it was Hilkeford again, called The End of ICT. Well, it hasn't quite happened yet, but people are still going on with ICT as well. So anyway, yeah.
No, special relativity is correct. You can't make an atomic bomb without special relativity. Don't make the mistake of thinking you can go back to Newton. You cannot. You can't.
I think there's some caveman somewhere, got a very big caveman, big strong caveman, got a very big surprise bashing uraniums together when he was banging his rocks together at some stage, without knowing anything about special relativity. So I don't think you're right there, Colin. I think you could probably make a big bang without understanding how it happened. I'm sure most people...
The T dimension is different, and we can only go forward in time.
Correct.
What about the W dimension? Can you go backward in W?
No. Haven't John explained to you yet. W, X, Y, and Z are all the same. It's just that we choose which ones to call the ones that are in our plane.
So the W dimension is more like our normal X, Y, and Z dimensions. It's
Yes.
less similar to T.
Yeah, it's just all mixed together. They're just all mixed. You don't know which one is which. I mean, X, Y, and Z. X is an X because by rotating Y thing into X, Y becomes X and X becomes minus Y.
Mm-hmm.
So yeah. I think the key is, and what we should all be looking at, and what Colin's looking at here, is that we should be looking at not at what we do know or think we know from any theory, but where it doesn't work. And when you start getting something which is, what is it? It's about 20 or 30 standard deviations apart, this microwave cosmic background compared to the observations on supernovae. When they don't fit, then you should be going, well, they don't fit. Then you should be looking.
I think it's only 5 standard deviations. Whatever it is, it's big.
It's too big. Yeah.
It's much too big. There's a crisis.
Yeah. It's a crisis. Another crisis. We have that crisis.
Physics is in crisis.
Yeah, we have the spin crisis. We should make a list. That's what we talk on, a list of physics crises. All the physics crises. I mean, Chari's given one, I've given one, you've given one, Colin, so we could have a sort of multiple acts. Peter's given another one. Actually, who hasn't given one about Phillips? Garnet's given one too. Yeah, we're a bunch of crisis people here. That's what we do. We've got all these crises going on.
That's good for a panel discussion, maybe.
Yeah, which is the biggest crisis? Yes, which crisis should be most worried about? Yeah.
Well, perhaps
okay, we're getting away from. Sorry, what was that, Garnet?
Perhaps all the crises are the same thing, and of course I have my own skepticism about that. That we simply take mathematical formalism too seriously. Right? I mean, our accuracies are fantastic now. We get 15 decimal places, but compared to infinity, which is where we start with the assumptions, is rather a long way off. So, you know,
there's nothing real about the real numbers.
Exactly.
But I think also there is a problem even with those 15 digits of accuracy and such things as QED. That is claimed. When you start looking at sort of higher order effects there, where you're really not only hitting electron positrons, but you're also hitting particle antiparticles, and you have to, and the numbers you get depend on the number of quarks, for example. Chari was pointing this out. Then really you can fit whatever you like. You've got enough parameters there that you can get your 15. You can fit what you like. We played a joke on one of my colleagues at one stage, myself and a fellow. It's April Fool's Day, and this man was very serious about different kinds of effects that might be seen in quantum transport. So what happened is with him on the y-axis and me on the x-axis, we made a plot, and we put some oscillations onto the plot. We invented it by feel and by hand about what sort of effects you might see. And that morning, we seriously sort of phoned him up and said, overnight, there's been some very interesting data measured. And we got him down to have a look at this. And he was quite convinced we'd seen, I don't know what it was, I forget whatever it was, Weyl fermions or something, whatever it was, from something which we'd simply made up by twiddling knobs. So, but I'm not saying that quantum electrodynamics is like that really at all. But nonetheless, you begin to get to a stage where it is model dependent what you're putting in terms of the number of corrections you're putting in, and that can be. There are surprising things one can change in a gauge theory to modify the results that one gets that shouldn't really make a difference, people say, but they do. So I'm not sure about the 15 digits of accuracy in QED either. Anyway, that's a personal view. So
I still haven't appreciated the significance of gauge theory yet. I guess that's probably getting too far out.
I think there are quite a few gauge theorists who haven't really appreciated the significance of the difference between gauge freedom and between gauge invariant and gauge freedom, because a lot of people do a calculation in one gauge and then invoke a gauge invariance and say this must therefore be true in every gauge. But a gauge condition is actually a condition. And you always get different solutions with different gauges. And there are a lot of gauge theorists that don't appreciate that has to be the case. If you're working in the Coulomb gauge, you get spherical solutions. If you're working in the Lorentz gauge, you get plane waves. In a theory like Maxwell's equations, there are lots of solutions that don't exist physically. The equations are under constraint. There aren't enough constraints. You're missing a bunch of constraints. So you need extra constraints to get fixed solutions. And that's what, and the gauge constraints are some of the ones that come in just in Maxwell's theory. So if you're putting the Lorentz gauge in there, you're putting a gauge that for example, the 4 derivative of the potential, so the 4 derivative of the total potential, the 4th derivative of the 4 potential is 0, it's the Lorentz gauge. In the Coulomb gauge, you just have the spatial part, 3 dimensions, that derivative is 0 separately. So that you have different solutions to that. It's an extra constraint, truly.
I see.
But then people think that gauge freedom means that, but it doesn't. I mean, you get different solutions for different gauges. Okay, it's just another constraint equation. In my theory,
you need it to make Maxwell's equations work out from the differential equation.
No, to make Maxwell's equations better constrained. The thing about Maxwell's equations is lots of things satisfy Maxwell's equations that are not physical. For example, photons satisfy Maxwell's equations, but anything that's not a photon, that's not quantized with these h nu, also satisfies Maxwell's equations, but they don't exist. That's an example, although the gauge doesn't fix that entirely. So in Maxwell's equations, you have solutions which are spherical, for example, electron charge, and you have electric field, but you also have solutions which are traveling waves. In the radiation gauge, you have traveling wave solutions. So these are different kinds of solutions. But for example, in my equations, you have 4 extra constraint equations. You have 2 extra gauge equations and an extra constraint equation between current and spin. You have current spin constraint as well, which isn't strictly a gauge equation, but a gauge constraint, but is a constraint. So it's just a constraint. The gauge stuff is just a constraint.
Okay.
Okay. Any more questions for Colin? Sorry, I'm getting off the topic here again. Colin?
Oh, very interesting.
Any more questions for Colin? That was another beautiful talk, Colin, by the way. And you've got a whole series of, just for everyone's information, Colin has given me a list of about 6 or 7 talks he'd like to give on this.
No, I think you've had 4 of them already.
You had 4? Oh, you combine. Okay, good. Fair enough.
Can I ask one question to that, maybe generally, not just for Colin. Whenever I come across these red shifts measured to the, like a Z equal to 1000, for example, for the galaxies and so forth, I get very concerned about it. I'm trying to understand this. How can they really tell me the Z equal to 1000? I'm going from the like a nanometer wavelength to millimeter or micrometers. In fact, I'm going from visible region to infrared, far infrared regions. Do I still have got really a handle on what I'm seeing? And how am I calibrating that one to be able to say what I'm seeing, exactly what I think I am seeing? And does anybody have any feeling for this?
They've measured the temperature of the CMB very, very accurately.
No, but that's a different thing. We're not talking about CMB. So I'm talking about Z equal to 1000.
Yeah, so Z equals 1000 is the reduction.
How do they measure this? Doppler shift. And the Doppler shift means you're measuring the wavelengths or the frequencies.
Typical frequency of light from a galaxy is Z equals 1000 away from the CMB. And that's where it comes from.
That's what I'm questioning. How do I know that? That's what I'm asking. How do I know that? How am I measuring that?
Well, it's just a number, Jerry.
You just fit what you're seeing to thermal.
What are they fitting? No, okay. I'm an experimentalist. I know what I'm fitting, but I want to know what. Does anybody have any information about that? That's what I'm asking. What are they really fitting? Yes. How do they know that?
Yes. Yeah, the way you know it is what you have is a signature, for example, to hydrogen that has a series of lines. Yeah. And what that does is that whole
Lyman, Balmer, Bastian series, okay?
Yeah, so that whole lot gets shifted. And you can measure
all of them. They're measuring all of them. They're seeing all those lines. That is good.
I presume, I don't know, I'm not an experimentalist in that field, but yes, as far as I understand it, the whole spectrum gets shifted.
That's what I wanted to know. If somebody really measured those things, the way all the lines shift, of course we have got that information, I know that. But the question is, if just one line does not tell me anything, if there are about 10 lines, they're all matching with what I expect, then of course I know that Z equal to 1000 or 2000, 10,000.
I don't think anybody's measured lines at Z equals 1000, John.
I have never seen a data myself like that.
Everybody's measured lines at Z equals 1000. But what they do have measured is a thermal signature. You can get the temperature of something, very, very accurately from its thermal
From
signature.
black body radiation for idea. So
Yes.
from the black body equation.
Yeah,
We are getting the
black
lambda
body
is equal
radiation.
to lambda t is equal to constant 2.898 10 to the minus 3 meter Kelvin. We know that number. If that's what they're using, and
Yes.
then I had to ask her.
That's how you get the temperature of the CMB.
Yeah.
And then from the temperature, you can tell how much it's redshifted.
I'm
You don't
not
actually
sure.
see lines in the CMB.
No, it's
It's a pure thermal signal. Whatever it is, 2.7 degree Kelvin, roughly.
Okay, I got to check that. I myself am not very convinced.
But you've got measurements up to Z equals 8 with quasar radiations. You've got very, 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 very shifted. Z equals 8 is a long way away.
Z equal to even farther. Anyway, that's fine. I have to struggle with this. I've been thinking about it for some time. Thank you.
Okay.
Does anybody here actually support the standard model cosmology?
Silly question, Peter. Of course
I
not.
think it's just archaeology and not physics at all.
It's
unbelievable.
It's mental archaeology. The problem is we got stuck in Einstein's mind. Einstein wanted to have a theory that covered the whole universe, and he forced everything so he could understand it into a three-dimensional, a flat three-dimensional space and an independent time parameter. And this is just amazing because he invented relativity where time and space are intermixed, and he separated them out again for the standard model. And can you imagine? That's what he did. That's Einstein's biggest blunder.
Not the fact that he didn't put the cosmological constant into De Sitter.
The cosmological constant, that's just curvature. That's natural, completely natural.
I take it that we don't have anybody rising up to defend it, the standard model of cosmology.
Maybe we should stick this up on the front of the website then. This is an almost necessary condition to join Quicycle.
No, it's fine if somebody wants to defend it. But people would like to know what the arguments on which they would defend it.
I think the whole thing has become really a standing joke for anybody who really knows.
Absolutely.
What the whole...
Well, I mean, as I said about the inflation field, it's pure fantasy physics.
Oh, that's terrible. That's inflation nonsense.
Yes.
It just suddenly happened for no reason. It's ridiculous.
No, it happened because you had to get from naught to large in next to no time.
Well, as somebody who's looked at quantum fluctuations for quite a lot of his career, the idea that those things could produce spots that are bigger than any galaxy in stuff that you can measure in different directions is just completely and utterly unbelievably unbelievable. So, so quantum fluctuations, yeah, what's it? Oh, it must be quantum fluctuations. It's what? Exactly what you say. I mean, where? Anyway.
Nor is there a single model. It's changed by the year.
Yeah.
Completely changed overnight, many times. There's not a single model of it. It's garbage.
It still has a point singularity, the Big Bang. And until we've got rid of that, we don't have a different model.
That is ludicrous.
It is.
Well, I think everybody here doesn't really, not just doesn't support that model, but just thinks it's a complete, it's worse than anything you can read in any ancient text, 5,000, 3,000, or however how many thousand.
Oh, the Pope loves it. The Pope loves it. It proves creation.
Come on. I mean, okay. Let there be light. Okay, fair enough. You know, light, cool, yeah, but okay. In the beginning, there was absolutely nothing, and then suddenly there was an enormous explosion. Oh yeah, right, cool. Tell me another one.
They don't say there was absolutely nothing.
Yeah.
There was infinitely dense energy.
Ah, yeah.
But they used to say there was absolutely nothing, but they changed the model. But they changed the model by the day, certainly by the year.
As you said, there is no one model at the moment. There are as many models as there are people.
Standard cosmological model. There just isn't one.
But the observations are, everybody agrees that they're moving towards De Sitter space. It's now standard belief, or standardly stated, that these latest observations show that the universe is moving towards De Sitter space.
I can say what I don't I could say what I don't like about thinking about having just a single parameter A here, a cosmological constant. I think that's too simple. I think the cosmological constant is not a constant. I think it's a variable thing, at least in the way that I'm looking at one of the previous talks I gave, where I was looking at these about what dark matter might or dark energy might be. Then it's a variable. Then there's a cosmological constant which on average could be A, but which would be variable in different places. So that's where my view would differ a little bit. It's not a constant, but it's something which has which is dependent itself on matter, on local matter, on frame dragging, amongst other things, on the local material. It's not a.
Oh, well, I didn't put any matter in there at all. But
no, I know.
You put matter in. Everything changes. I agree.
Yes.
Yeah.
Yes. Yeah.
You've got to build Mach's principle in. You've got to build it in somehow.
We have. Actually, we need to have at some stage a discussion where we get Viv involved in this as well, Colin, and talk about both the possibility of both having frame dragging going on and having gravitation going on and having and seeing if, because in a typical in your view, in a typical universe, we have both the frame dragging of the system going around, but then you also have the gravitational rotation near the center. And then everywhere else, of course, you have both happening. But discussing the whole thing there, I think it would be an interesting discussion to have a look at the different models that other people, Lyndon Ashmore as well, have on where the whole view of the universe that we have comes about in terms of whether or not these things are contradictory or they can exist at the same time, that there is evidence in this area for that aspect of it, and then for the frame dragging here and gravitational effects, general relativistic effects, or extended general relativistic effects elsewhere. Where are the contradictions between the various ways that we're looking at this stuff ourselves within our own group, not just with the standard model?
It would seem to me that if each of us is within the Hubble bubble of our perception, but the universe extends out beyond that, and the universe is pervaded by gravitational fields and photon fields, then one would imagine that in our local Hubble perception, there would be different states that would be dynamically flowing through this local part of the extended universe, which means we should expect to see changes in rates of expansion contraction locally. No?
I think our Hubble bubble's kind of got bumps in it. If you look around, looking at the cosmic wave microwave background, it's not quite a round bubble. It's a sort of a lumpy bubble, and it's interesting to look at the lumps.
They're very, very small, actually. They make them look big because they've measured them, but they are very, very, very small.
Do you have a feeling for the percentage difference between the deepest, what are we talking about, RMS variation? It's not a percent, is it? It's like 10 to the minus 2% or something, isn't it?
10 to the minus 5, I think.
10 to the minus 5, that's small, okay.
I think it is. It's thermal, that's what I said, it's thermal to better than 1 part in 10 to the 5th. So these are deviations from thermal.
Better than 1 part in 10 to the 5, so it's 10 to the minus 3%. Yeah, okay, righty-ho, good. Okay.
You can look it up.
Okay, plenty of food for thought once again. Well done. Thank you. Let's thank the speaker once again for some more exciting stuff. Thanks, Colin.
Thanks a lot, Colin. Great talk.
Thanks, Colin, again. Lovely talk.
Interesting.
Bye-bye.
Thank you.
Bye for now.